are talking about what is information, reversibility, and simulation.
Well, I want to thank Bob and the organizers, particularly for inviting me. I want to do that particularly because it's not at all clear anyone else will. So let's proceed. This talk is really in two parts. And the first part is asking the question, what is information? And so what are we up to? Well, as a physicist working in quantum information science over the last 15 to 20 years, it's clear that the term information has several distinct but related meanings. This is motivated in part by physics, by the fact that we want to use the same word information to describe certain aspects of quantum physics that we use to describe things having to do with classical probability theory and so on. So clearly there are several distinct meanings, and so what I want to try to do is take this experience and identify some universal ideas about the concept of information. How do we know that it's information? How do we know that the term information is an appropriate term? And so this is a categorical way of approach, a categorical way of thinking, which more in a moment. I want to point out that we're not necessarily going to quantify information in every circumstance. We won't necessarily come up with a quantity and say, yes, this is the information. Sometimes we will identify useful quantities that will tell us things, but in general it might not be the case that a single numerical quantity will capture the notion of information that we want. And also I should announce to you what my criterion of usefulness is. The criterion of usefulness is, of course, that this way of thinking is a good way of thinking if it generates interesting problems. If it generates interesting questions for investigation. Things that we want to know, but we didn't realize we wanted to know ahead of us. Now, I should tell you that I don't know much about category theory. I'm a quantum physicist by training. I know less about category theory than almost anyone else in the room. And so that gives me the very difficult task of trying to give a talk that's at least inspired by in some category theory, but not knowing on which side of that line between the profound and the trivial that I will be walking on. I comfort myself with the reflection that if I am not able to instruct you, I may in some sense at least be instructive, as an example of what a naive quantum physicist would think. And so my strategy for this, to respond to this, is to immediately change the subject to another subject about which, in fact, I know even less, and that is beer. The difference between category theory and beer, I've tried them both in category theory. I like better, so I think I know what that is. All right, so here I want you to think about a row of jars, and in the jars the jars contain various amounts of beer or water, or some of them contain mixtures of beer and water, and some of them are empty. Right? In fact, almost all of them are empty because, for convenience, it's easiest to think of this as being a countably infinite collection of jars, and only a finite number of them have anything in them at any given state. Okay? So this is our system, and a state of this system is a distribution of beer and water among the jars. Okay? All right. So now, what are we going to do? Well, we're going to make changes in the state of the system. We're going to perform operations on the system, and the allowed operations include the following. We can pour some or all of one jar into another jar. And combine this to a larger transformation, to a more complicated transformation. But this is all we can do. We can't run the contents of a jar through a reverse osmosis filter or something and separate things out. Now, this is all we can do. Now, if you reflect on this, we're not very long. In fact, you probably already concluded on this. You'll know that there are at least two kinds of state changes that can happen to the jars of beer and water. One of them is a reversible change. If you transfer liquid from a jar to an empty jar, or from one jar to another where the contents of the jars are the same kind of stuff, the same percentage of beer, then you've done something that's completely reversible. You can reverse it by simply pouring it back, pouring the same amount back, and you restore the original state of the system. That's a reversible change in the model. But then there are irreversible changes in the model, and those would include those in which we transfer liquid to a jar with a different contents. For example, we take some beer and we pour it in a jar that contains water. We mix water and beer together, or even mix together two different mixtures of water and beer. That's irreversible. No amount of pouring will restore the original configuration of beer and water in the jars. It's an irreversible transformation. Now, two things I want to point out about this. One is that whether or not a change is reversible depends both on the initial state and on the transformation performed. It's not a question of the transformation being some state function that is an invertible function. No. It's a question of whether this particular state, which has undergone a state change, can be restored using the set of allowed operations. That's the question. And also, there are obvious analogies here to thermodynamics. In fact, more than analogies, we talk about the entropy of mixing and so on. There are reversible and irreversible processes involved. Obvious analogies to thermodynamics. But aside from this remark, I just want to reflect that even a person who doesn't know much about beer knows that in one of these irreversible changes, something has been lost. But what is it exactly that has been lost? Well, it's not an easy question to answer, but let me give you one answer, which is the first thing that occurred to me, actually. And that is, we can define something we'll call the unmixedness of the state. Okay? Here's the unmixedness of the state. It's the sum over all the jars of the amount of liquid in the jar times the square of the fraction of the contents of the jar that's beer. And where there's nothing in the jar, we take this term to be zero. And why the square? Well, any strictly convex function would be just as well. But the square is easy. So we can. So this is the unmixedness of the state, and then it turns out that no matter how you pour contents from one jar to another, it's easy to show that you can never increase the unmixedness in that way. Any possible transformation, any allowed transformation, will never increase the unmixedness. It might leave it the same, or it might increase it. It might increase it. Oh, sorry, decrease it. Right. It might leave it the same, or you might lose some unmixedness. And since you can never increase the unmixedness, if you lose some, you're sunk. You know for sure that the operation is irreversible. So, you know, if you set your jars up and you walk away and come back and somebody has done some things to the jars, and you say, oh no, am I ever going to be able to put it back the way it was? One thing you can do is you can calculate the unmixedness and see if it's gone down. But in fact, the unmixedness is even better than this. It turns out that a transformation is reversible if and only if the unmixedness has state, and that some state changes are reversible, some are not reversible, and there's at least in this case, there's a function, this function u, which helps us to diagnose whether or not a transformation is reversible or not. Okay, and so those are the characteristics of the Beer model that I want to point out. Now, what does this have to do with information? Well, to answer that question, I want to take a common example of information, and that is just this morning I was reading my hometown newspaper online because somehow they don't get the Mount Vernon news from Mount Vernon, Ohio, in Oxford the same day. Anyway, so of course, what I actually got was an electrical signal. But somehow, what it meant was today's paper. All right, and of course there are I might have gotten different signals, and they would correspond to different possible configurations of the paper. And the first point I want to make is that somehow the electrical signal and the tangible newspaper that shows up in my driveway have the same information. Somehow information is something that is the same, independent of its representation, physical representation. And so that means information is something that's, a newspaper is equivalent to an electrical signal. It's because I can turn the newspaper into an electrical signal by some physical means, and I can turn the electrical signal into a newspaper, effectively, by some physical means. There's a way of going from one to the other. And of course, information is what's invariant of that kind of transformation. And of course, that's just like topology or something, where two things are the same topology if you can take an allowed transformation and transfer from one shape to another. Okay, but I want to point out actually something else, something more specific about this, and that is that in some sense the information in the electrical signal, and this I'll call this electrical signal the signal, and then the newspaper, which I will always imagine to be some physical newspaper back in Ohio, the newspaper is the referent, the thing the signal refers to. What I want to point out is that the information in the signal resides in the correlation between the signal and the referent. If the signal I received had no correlation with the state of the newspaper, then I wouldn't say that it had any information about what the news was back then. So, this leads us to communication theory. So what's communication theory like? Well, we have a referent, and I'm just going to imagine that the referent is a real physical system. If there's no physical system standing for the referent, then it's not clear what you mean by the signal having the right information or not. But anyway, so you have the referent and you have the signal, and then all kinds of things happen to the signal on its way from the server back at the Mount Vernon News to me. There's distortion, there's noise due to the environment, there's all kinds of things that happen, and then when I receive it, I do all kinds of things to it. Maybe I do some signal processing, and I digitize the signal, and I do error correction, and then I effectively reconstruct the newspaper. Now, the whole point of this is that everything that actually happens to the signal. Everything that happens to the signal. There's this referent, which stays at home, and then the signal goes abroad, and stuff happens to it. The channel acts on it. There's data processing on it. So, here's what we've got. We've basically got a couple of random variables. There's the signal, which has various values abstractly, and the referent, which has various values abstractly, and there's some, and we want to say that the signal carries information about the referent. That's the kind of language we're going to adopt. And that relationship between them is represented by some joint probability distribution over various states of the signal and referent. I'm now using a sort of a classical probability theory description of things. I'll talk about quantum mechanics in a minute. an example. I just did an animation there to show one possible operation is a permutation of the rows, the same permutation of the elements of each column. That's a possible process. And if that process takes place, it's actually easy to undo it because we can then just apply the inverse permutation to each column, same operation to each column, and we undo it. And so that means that this kind of row permutation is a reversible operation. And if it's reversible, that means that this operation doesn't cause any loss of information because I can restore the original state. And somehow the original state embodies the information. On the other hand, it might be that these conditional probabilities are sort of more spread out. They effectively blur out the distribution in some various ways. And if this happens, then there's no operation only on A, no operation that is the same on all of the columns that can restore it. For example, I might want to restore all the weight in that first column to the first row. But any conditional probabilities that did that would do the same thing to the second column, and that would be wrong. So there's no operation that can undo this, and so this blurring of the rows is an irreversible transformation on the joint state. We've lost something. We've lost information. Now, okay, so this means that there's a kind of a natural information structure associated with this problem, communication theory. And the structure looks like this. What we have is we have a space of joint distributions over A and B. Okay, here's the space of joint distributions over A and B, and here's a distribution P that represents some information, some correlation between A and B. And it doesn't have to be one of those diagonal distributions. It's just some distribution, joint distribution. And then there are I might have a map involving conditional probabilities acting only on the signal that takes me to different distributions. And the set of possible operations includes all of the conditional distributions acting only on A. That's our set T, our identified set. And I'll use the arrow. I know you like arrows, so I'll use the arrow to mean that one distribution can be turned into another by some operation in this allowed set. And of course, P and P prime are equivalent, and therefore we're going to say they have the same information if I can turn one into the other and the other back into one. The transformation that takes P to P prime can be reversed by an allowed operation. And so what I want to say is that this is a natural information structure, a natural way of thinking about the information in this, the information represented by these joint distributions. It induces a partial ordering on the equivalence classes of the distributions, and we can characterize reversible and irreversible transformations within this set of allowed operations. Okay. Now, in order to help me understand the information structure, it would be nice to have a quantity or so to help me, some way of characterizing these things by a number. And it turns out there is such a quantity. In fact, there are lots of quantities like this, but I'll just talk about one. And the generic name for these is a monotone. And basically, a monotone is a functional of these distributions, and it's called a monotone if it can never increase under the action of an operation in T. It can never increase. And so there's a famous one in classical information theory. It's based on the Shannon entropy, which we have here on the left. But the one I want to look at is the mutual information between A and B, which is a measure of the degree of correlation. An information theoretic measure of the degree of correlation. And it turns out that the mutual information is a monotone. If we only manipulate A, the mutual information can never be increased. actually reversible if and only if the mutual information is not changed by the operation. So actually, this is not just a monotone. It's better than a monotone. It's a monotone that allows us to exactly diagnose reversibility and irreversibility. So we're going to call something like this an expert monotone. That sounded sufficiently impressive. Okay, so mutual information is an expert monotone, and that's one of the good things about it. It allows us to determine whether, for example, the action of the communication channel on the signal has introduced a state change that can be undone by further data processing. The mutual information will answer that vital question, or whether something is reversed. Okay, let's do quantum communication theory, and we're going to do quantum communication theory in exactly the same way. We're going to have a couple of quantum states. We're going to call them the signal and the referent. A is the quantum signal, it's some quantum system. B is the quantum referent, it's some other quantum system. And all of the drama is going to happen to the signal. The referent won't participate. The composite system is described not by a joint probability distribution, but by a joint density operator. And this density operator might include classical correlations. You can do classical information theory this way. You like it, include entanglement. I don't care. There's just some joint state. And we're going to restrict our operation T to all operations that you can do on A by itself. All trace-preserving, completely positive maps of the form E tensor the identity. So these things can change A around, but nothing happens to B. Okay? Now, in this situation, we're going to say that somehow, in some sense, A carries quantum information about B. So, what's the information structure? What does this setup give us? Okay, well, so let's look at this set. This is our set of all possible joint states of A and B. And in addition, we have the set of all of our allowed transformations, which are things that can only act on A. A is going to be subject to the dynamics of the channel. A is also going to be available for our data processing techniques afterwards. And it turns out that you should think of this set of states as being composed of a bunch of affine hyperplanes, and so it's all foliated like this. And one leaf of this foliation, what is that? Well, that is the set of all joint states with a given rho B, a given marginal state for the referent. And the point about that is that no operation only on A can change this. No operation on A can change this. This is the no signaling principle in quantum mechanics. And that means that if I'm only considering A operations, I can't go from one leaf to another. I stay on the leaf. And so I can just think about the leaves one at a time. That's easy. Okay? All right, so let's take a look at what the leaf looks like. Remember, our operations are operations that can only affect A. And this is the set of states, all possible joint states, that have a particular rho B, so that's fixed. All right, so what have we got here? Well, let's see. Some states can be turned into other states, and that induces a partial ordering of equivalence classes. That partial ordering has actually a set of minimal states of minimal information, if you will. And these are states that can all be turned into each other, and any joint state can be turned into one of these guys. And they consist of the states with no correlations, the products of two density operators for various omegas. This is these are the states of minimal information. They're at the bottom of the leaf. And then there's a set up at the top of the leaf, the states of maximal information. And these are things that anything in the leaf can be made from. That is to say, these are all equivalent to each other, and you can turn one of these into anything on the leaf. And what do they include? Well, they include all the pure joint states of the composite system. And it turns out that any such pure entangled state can be turned into any other one by a unitary transformation, which is in our set of allowed operations, acting only on A. And these are different purifications of the same B state in quantum information parlance. And so these are very good. It can also be shown that you can turn one of these into any mixed state with the same density operator for B by an appropriate time.
Pure state also can be product state, right?
If the pure state, if this is a product state, then the leaf, a product pure state, then the leaf is a special leaf. It's the leaf for a pure B state. The leaf for a pure B state. And those are trivial. Everything's equivalent. These two sets are in fact the same if the B state is pure. Everything's equivalent to everything. Quite right. And then of course, if the overall state is a product state, then in some sense there's no information in the correlation between them, so it's a trivial case. Okay. I have to mention to you, some of you are probably thinking this, but it's really true, that there may be other things in this set of maximal states. There may be some mixed states up there. This is a consequence of quantum error correction. It's kind of interesting, but it's a side note. I just don't want to make you think that those are necessarily all product states. Some situations they may be, some situations you might have some mixed states in there as well. Okay. Now, so to diagnose reversibility and irreversibility, it would be useful to have a monotone. And so we can build a monotone, and a simple one is built out of the von Neumann quantum entropy. It's not the von Neumann entropy, it's this thing, something that's often discussed, called the coherent information. And the coherent information is the entropy of system A, the signal, minus the joint entropy of system A and B, the composite system. Now this quantity cannot, the analogous quantity classically, can never be positive. But it can be positive quantum mechanically because of entanglement. And it turns out that the coherent information plays some of the same role in quantum information theory, especially communication theory, that the mutual information plays in classical theory. So let's talk about the properties of I. It turns out that I provide you a coordinate to help map out the leaf, and it turns out that for any operation that acts only on A, the coherent information is non-increasing. You can't increase the coherent information by applying the operation only to A. And so I is a monotone. And so therefore, if I goes down, we've lost something and we can't go back. But I is even better than that. It turns out, and this is a quite deep fact about entropy, that I is an expert monotone. That an operation is reversible if and only if I is unchanged. This is quite general. And for the quantum information people out there, this is a way of stating the equality condition for the strong subadditivity of equal. Okay, so I is expert. It completely diagnoses whether or not we can undo the transformation. And that's true whether the initial joint state is some complicated mixed state, or if it's a pure entangled state, or anything. This is true. Here's another interesting thing, which is really an aside in this talk, but I think it tells you that we may be able to do more. What if the coherent information goes down by just a little bit? You lost some coherent information, but you only lost a little bit of coherent information. You only lost epsilon coherent information. What happens? Well, it turns out we know the answer if you start out with a maximal state on a leaf. We know that if the coherent information goes down by epsilon, then we can restore the state to a high fidelity, a measure of closeness. Restore the original state to a high fidelity, a fidelity that's like 1 minus the square root of epsilon or something like that. I even tells us at least something about approximate reversal of the operation. You might ask the question, well, suppose we'll start out with a maximal state, and you only lose a small amount of coherent information. What's the answer? And I can't tell you the answer. As far as I know, that is not known. So, first interesting information theory question generated here. Okay, so here we go. Finally, I got to the most important slide of this talk. Here it is. What's the lesson we've learned from classical communication and quantum communication and Beer? And that is, our concept of information depends on 2 things. It depends on the set of possible states of our system, and it depends on the set of possible operations on our system. And this set of possible operations should be a semi-group community. I guess that is a boundary, right? The fact that I would ask such a question illustrates the point I made earlier about me and categories. Okay, so, all right, the set of, yes?
Can I add? Does the operation to correct the error not belong to T? Otherwise, how would we increase?
The operation.
Sorry, I'm talking about the previous slide.
Previous law. Yes, it does.
Last line.
Here?
Yeah, on
Yes.
this last line, we say that.
The last line, we can approximately reverse the operation? Yes, by an operation on T. If you can do a joint operation, you can always prepare the original state again.
So how can the last line and the third last line?
The question is whether things are exactly reversible or approximately reversible. And the notion of approximate reversibility will have to effectively introduce a metric on a leaf. I'll have to be able to tell you when 2 states are close together. It's because everything except the final line here, I'm either asking whether I can get exactly the original state back or not. And here I say, well, can I get to something nearby the original state? And the answer is, at least in some cases we know, that even if there's a little bit of loss of coherent information, we can return to something in the neighborhood, in a small neighborhood around the original state.
So we are not increasing I by using an operation.
Oh no, we go back to a state that has I no bigger than I minus epsilon. Okay?
Right.
However, that state is close to in the metric on the leaf, close to the original. Yeah, right. I'm sorry, I wasn't clear about that. Okay, so all right, so we have this set of possible operations, and the point is that that set, the set of possible operations, is the thing that determines what we mean by the concept of information. The concept of information is derived from the set of possible operations. And indeed, it's the limitations on that set of operations that makes things interesting. If you can make any state from any state, the information theory is trivial. All processes are reversible. Nothing is lost. But if there are limitations on the set of transformations, the set of operations, then things become quite interesting. Okay, so in physics we do this kind of thing all the time. Here's 3 different information theories for you. One of them is the one we just talked about. We have a pair of systems, A and B, and we can only manipulate A. And then we get what I've called communication theory, where I interpret A as being some signal that goes ventures out into the world, and B as some referent that stays at home and sort of roots the correlations. But you can also imagine you had some gigantic system with trillions of degrees of freedom, but all we can do is manipulate a very small number of macroscopic degrees of freedom. And we can ask, when are transformations reversible or irreversible in that situation? And then we're talking about thermodynamics. I put a question mark after that because I haven't yet derived all of thermodynamics from this concept. We're working on it. But another one that you've probably heard of is, suppose we have a pair of quantum systems, A and B, and we can do local operations on either one, and we can also send classical messages back and forth classical result of one measurement to let us choose which operation to do over here. Local operations and classical communication. Now, for classical random variables, if you can do this kind of thing on the two systems, you can do anything. This would include all operations. Quantum systems, not quite, and the resulting concept of information is quantum entanglement. This is in what sense entanglement is a kind of information, because it captures something about what transformations are reversible and irreversible under a restricted set of operations. Okay. So now we move to part 2 of the talk, and that is to take this kind of idea and to ask, what is computation? What is computation? What is information processing? And the first thing I want to note is that information processing must be a physical process. It's always realized by the dynamical evolution of a physical system. There's no disembodied computation. And by concept of information processing or computation includes all kinds of things like communication. Communication between two systems accomplished by some interaction, that would be a kind of computation. Perhaps to do some useful task. And so what we want to ask is how we're going to classify different communication process or computation processes. That is to say, when can we say that two dynamical evolutions do the same computation? We had a notion for when two states have the same information as when we allow transformations by turn one state into another. And that way, the newspaper can be turned into the electrical signal, which can be turned back into the newspaper. But now we're asking the same question dynamically. The key idea here, of course, is that one process can simulate another. So simulation is a pretty straightforward idea. We have some system states, and under some map E, they map to the image of that set of system states. And what we want to say is that a dynamical evolution F simulates E, which can also represent by an arrow, on G, the set of states, if there exist other maps, C and D, which can make this diagram commute. Now this by itself is too primitive. This picture is too primitive. I'm going to have to add one more piece. But right now, this is the sort of primitive notion of when F can simulate E. It means I can accomplish the transformation E going by way of F. And this is in fact what we always mean when we talk about actually doing a computation in the real world. What we mean is we have the state of some abstract computer, and then it has some abstract function that leads to some abstract result of the computation. But what we really do is we prepare the state of a physical device based on the abstract state we're interested in. We have that device undergo some dynamical evolution, and then we make a measurement to read out the result, and we say that this dynamical evolution has performed the computation provided this commutes. Okay, so let's think about communication in this way. Our set of states is a set of joint states, rho A, B. And our process E is an interaction between these two that accomplishes some communication task, that transfers of information, whatever we want to say, that does something that I specify. Okay, now, if I want to ask whether F simulates E, it would be cheating if I allowed the maps C and D to do the work. Okay, that would be cheating. That would not really give me a very interesting notion of what can simulate what. I wouldn't want it, for example, I wouldn't want something that involved no interaction whatsoever between A and B to be able to simulate the communication of a strong interaction between them. So what I want to do is I want to make restrictions on C and D. Make restrictions on C and D. And I'm going to say that in this case, the appropriate thing to do is that C is just some product now. I can, it's a coding operation. I do something to C and D, to A and B rather, independently. And so that's and the same thing for D. And then I know that the interaction between A and B is only contained in F if I follow the lower path through the diagram. Similarly, suppose I want to think about computational complexity theory. I want to ask the question, if I want to compare the cost of doing some computation, I might measure the cost of the number of computation steps, or the size of the memory of the computer I need, or the amount of communication between separated parts of the computer, whatever. I want to measure some cost of the computation. And so, if I want to find out whether F can properly simulate E, I don't want to cheat. If I want to compare the cost or length, but I don't want to hide the cost in C and D, the coding and decoding acts. And so what I'll do is I'll require C and D to be in some sense that I'll define depending on the problem to be short or cheap computations. And then I can actually compare these guys, and I can find, for example, that it really is shorter somehow. It really takes less resources to traverse the lower route than the upper route. I can really compare the efficiencies of F and E. Okay, so in each of these two examples, the communication example, the computational complexity example, the thing that I need to do is I need to restrict the C and D maps. I need to restrict them to a subclass. So what I've got here is I've got that E and F are in some big C, the set of computations, and C and D are in some subset of C. The coding and decoding operations, the translations from one to the other. And so my notion of computation is going to depend on C. It's also going to depend on T, the set of translations between different dynamic processes. And then we can ask the question, we can say, given C and T, when can F simulate E on the set G? Okay, so let me give a simple example, because at this point I'm lost. And if I'm lost, then you must be lost. So let's consider a pair of qubits, and our states are pure states of a pair of qubits, our C is the set of all 2-qubit unitary gates. For example, the C0 gate, which some of you may have heard of, would be a possible unit. And T is going to be a subclass of this. T is going to be a set of separate unitary gates on each qubit, where I do an independent unitary operation on each qubit. That's a subgroup. So now I'm asking the question whether V can simulate U. And that's asking the question whether there are unitaries that allow me to represent U in this way. I precede and post-process my qubits using unitaries, single qubit unitaries, and the only interaction might occur with V. So that would be a kind of question that we would ask in this thing. If this is true, if these things can be made equal, then we say that V can simulate U. And it turns out in this case, U can also simulate V. That might not be true in general, but in this case it is. Okay. So, of course, we found out with information that it was really handy to have some numbers, and really handy to have some quantities that we could calculate then those calculated quantities would tell us something about whether one state could be transformed into another. Here I want to calculate quantities that are going to help us calculate whether one process can be simulated by another process. So here's, and I don't claim that these are the only ones, I'm going to tell you one way to build such things. And so I'm going to suppose x is some function of my initial state and my operation, which means it could be a function of the final state on that top line there. But in general, it's a function of the initial state and the operation, such that if I extend the operation by composing it with a subsequent operation, then this quantity cannot be increased. In effect, it's a monotone for things k, all those k's are in t. It's a quantity which is kind of a monotone for operations in t. It can't be increased by the subsequent action of one of these short, cheap translation maps. Okay, so we're going to assume this. And now we're going to define the x star, which is now a function only of the operation, to be the maximum value of x over all the possible input states. The maximum value of x over all the possible input states. Now, I think in terms of finite dimensional quantum mechanics, so it's compact, so it's a maximum, not just a so I have this. What can I say about x star? It's a kind of a if x was an information measure, being a monotone, then this is a kind of a capacity measure. Okay, a maximum of the information measure. Well then, it turns out that x star of e, well, it's equal to x star of that composition because the diagram commutes, which is we can tell that it's less than or equal to x star of f tensor c because x is never increased by subsequent processing, and because x star is defined as a maximum over inputs, pre-processing never increases this. I'm assuming that e of b is inside b, and so this never goes up. This never goes up. And so this is how we build a simulation monotone. And the moral of this is that f can simulate e if and only if x star of e is less than or equal to x star of f. Not if and only if. We don't know if. And in fact, in general, that's quite difficult. Only if f has more x star than e does. And so this quantity can help us diagnose whether one computation can simulate another, one process can simulate another. Here's a simple example, which I have you have to tweak some of the definitions to make the example this simple, but I thought this was worth looking at. Once again, we have the same examples here. But what we're going to do is we're going to imagine instead, and as I said, you have to tweak the definitions of that. B is the set of product states. I'm restricting the set of input states. And so I have to, like I said, I would have to tweak the definition. That's all right. I just want to give you the idea. And x is the entropy of entanglement of the output. The entropy of entanglement can't be increased by independent operations. The entropy of entanglement for a pure state is the entropy of the density operator for one of the systems. And then it turns out that if we take the maximum entanglement produced by the game U, that's a simulation monotone. That is something that will help us diagnose whether one thing can simulate another. So the C0 gate has an x star of 1 E-bit. So if we have another gate which has an x star of only half an E-bit, that might be a control gate that does something that's not quite as transformation on the target bit as the node. Then we can tell that that gate could not simulate the C naught gate under this structure. Okay, and therefore V can simulate U if and only if X star V is at least as big as X star U. We get that. Okay. So here's some intuition. It's good. It's like a winding up. That's right. So for information, we had a set of allowed states, we had allowed operations, we had monotones that were non-increasing under the set of operations. For computation, we had a set of computations, and we had also a subset of those computations, the coding and decoding operations, and the quantity that we built was a simulation monotone, something that was non-increasing under C, or even just under T is good enough. So, M here, this monotone, is something like the information content of the state with respect to the operation. But I don't want to identify it as information content, but heuristically it's something like that. And in a similar way, X star is something like the information capacity of E with respect to the computations of the translation. And you can't simulate a high capacity operation with a low capacity operation. All right. So to sum up, our concept of information depends on the set of operations that we may perform. And information may be preserved if the operation is reversible on that state, or it may be lost if the operation cannot be reversed. Monotones help us distinguish these situations. And then computation is based on the idea that one dynamical evolution can simulate another dynamical evolution. And capacity quantities that are made from maximizing monotones can help us distinguish whether this is possible. So I just need to tell you, if you're building information theory, you just barely started, you haven't done anything almost. You haven't talked about, if you do information theory, you find out that lots of things are about asymptotic limits, large numbers of systems, fidelities being close to one, but not exactly one. And this is not the algebraic, this goes to that, this is these approaches one. And we haven't talked anything about quantifying the resources necessary to perform information tasks, although it would be quite possible to do so. We haven't talked about the classical communication part of global operations and classical communication. Notice that quantum entanglement concept of information depends on having a prior classical concept of communication. We haven't talked about really much about measures of entanglement or fidelity or nearness, or the complexity of operations or things like that. We just sort of waved our hands at all those things. We haven't done any real category theory, of course. We haven't talked about Bayesian approaches to thinking about quantum states and so on. We haven't talked about the connection between beer and computation. Serious, we haven't talked about a computation theory based on these kinds of transformations that we talked about with the beer model, but maybe we can talk about the general version. And then pretty much the details are pretty much everything. We sort of sketched out a kind of a program for generating questions. And with that, I'd be happy to answer questions.
When you were talking about managing entanglement, if I have two mixed states, sometimes good idea to use negativity. Can you use negativity or negativity? Is this useful idea?
Yes. As long as it's a monotone in the appropriate.
In the beginning, you said that coherent information will not increase under local transformation. Does negativity have the same property? Do you know?
So I believe that's right for negativity. I think the answer is yes. But there are many monotones known, and each of them would be suitable as a kind of one of these kind of auxiliary quantities that help us understand when things are reversible and when they're not. question of whether the transformation is reversible rather than quantifying the information, I think.
You said earlier on that translating or transferring paper newspaper to electronic form was a reversible operation. By and large, that isn't, because there are plenty of things that there are about the physical newspaper that there aren't in the online version. So what is it? I'm worried that the only way we can say they are similar, that they have the same information content, is by already having a notion of information.
Right. That's quite true. And mostly that has to do with the fact that my different newspaper states are rather coarse-grained. That is to say, the different values of my random variable representing the newspaper already include coarse graining about whether the edge of the paper is this shape or that shape. And so I have indeed assumed that I can identify two different physical states of a macroscopic system with trillions and trillions of degrees of freedom as the same newspaper state. That's quite true. But it basically amounts to coarse graining, and that's I think it's a different sort of problem. It's an interesting problem. How do we coarse grain? How do we understand? As a practical matter, we do somehow know that the newspaper I got on my driveway and the newspaper my neighbor got are somehow the same newspaper, effectively.
But isn't this the problem, that we have an intuitive notion of information, we're just trying to pin it down? And so I'm concerned that you're needing that pinned down version of the concept to be able to define the version of the concept.
In some sense, you're right. This structure is relative to is built based on the ability to take two physical objects and determine whether they represent the same newspaper state. But that process is in some sense conventional. However we define that, then we can talk about a communication theory.
But if we've already got that, we've got a notion of information, so the rest of the
Not exactly, because first of all, it compares newspapers to newspapers, and the whole point about information is that information. If you think about the physical representation of the news from Mount Vernon on its way here, there are a dozen different physical instantiations of that, and so that's a key concept of information that comparing newspaper to newspaper doesn't address. Secondly, that comparison has nothing to do with any dynamical assumptions, any dynamics. It's just, is this object in this state in the same equivalence class as a very similar object in another state? And so I would say that there's a lot in this structure that is not contained in the answer to that question.
Okay, so talking about the beer and water problem, in my intuition, if we had an ancillary system made of a lot of glasses of only beer and only water, we would make any operation approximately reversible in our subsystem.
Well, then you're adding a set of transformations that include reservoirs of beer and water.
Yeah.
And if you have reservoirs of beer and water and a drain, then suddenly your transformations can turn anything into anything, and you still have a theory. It's just a trivial theory that any configuration of beer and water can be, of course, constructed by pouring out all the stuff and refilling the jars with the appropriate amounts of beer and water.
Yeah, but for example, what about in the quantum case having a kind of reservoir that we can control? So not infinite. So there is a partial.
I haven't looked into the quantum beer and water problem, which I think I ought to. But to answer your question in the case of beer and water, if you include the state of the ancilla, it's still the case that if you include all the jars, the unmixedness is still a monotone. And if you provided you don't get to pour anything out, and so on. Okay, mixedness is still a monotone, and so if you take you could probably restore things by using up ancilla resources. It would still cost you some ancilla resources. You still have to lose some from your reservoirs in order to do it. And you can quantify that cost. How much do I have to pour out of my beer reservoir and pour out of my water reservoir to restore my jars to the right situation? It's all that is possible.
Is it similar to using quantum error correction in coding?
I think it's similar to using
a
thermal reservoir to do some of your work in a free energy problem. I mean, that's the way I think about it.
No, because I think more about having a part of the system which contains the interesting stuff, and another one that it's rubbish, I can throw it away whenever. But not an environment that is not controllable. So.
I see. In the presence of ancilla systems that are prepared in a particular way, in this case, pure beer and pure water reservoirs, it's often the case that things become very simple. So, for example, in the presence of a supply of E-bits, local operations and classical communications plus a reservoir of E-bits allow you to turn any joint state into any joint state using only ancilla resources in classical communication. You just teleport things. And so that's an example where if you provide too much of a particular resource, the question becomes a trivial question. And yes, it's quite possible to do that. I think that the analogy to the ancilla ancillas would be more like the use of empty jars. Okay, the empty jars of the ancillas, the ancilla analogs, in my view. And you can say, oh, well, I can always use some more jars to spread things out a bit.
Maybe just one extra glass.
Yeah.
So in the first half of your talk, you essentially said, what is information? It's a resource relative to a restriction on what I start with and a restriction on what I can do.
It's information is a resource. Well, resource counting is something I haven't done. I've simply talked about what transformations are reversible and what transformations are not reversible, and argued that's the key question about information, not resources. But, okay.
So then, what I was going to ask you, maybe this answers my question, is are you sympathetic to a view of computation that's sort of similar, that, if you ask, when do I know that some interesting computation has happened, I can say, well, it's, when I've got something relative to a restriction on, what I start with and a restriction on what I could do, I've got something interesting. So if I only have so much space and time and energy to commit something and so much computational complexity or algorithmic information, then if I've increased my algorithmic information, I've done a computation. Are you not sympathetic? Does that mesh with what you said here?
I'm powerfully sympathetic to that, but I think it's outside what I'm talking about. I think what I'm talking about is sort of the chapter before that. I really talk about resources very strongly, except in as much as there are various monotones floating around that tell you something